Good evening to all the students. Welcome to second week discussion for the Electrical Machines 2 NPTEL course. Uh, Last week we have discussed the basic principles of electrical engineering. Like we started with basic definitions of inductance and dot convention. Some polarities we have checked, and then we solved some problems on it. And there were some discussions about dot convention polarity as well. So I want to discuss some more concepts on dot convention so that you will also be clear about it, and then we will proceed to the second week's content. Since there was a lot of discussion last week on some little small confusions regarding dot convention, today the first session of this discussion we will discuss a little part about dot convention, even further deeper discussion into it, and that should definitely make everyone comfortable with the dot convention, and then we will move to the subsequent content. So with that, let's start this week's discussion. So yeah, to start with, let me just start with a basic definition of a coupled circuit, because to get the even deeper discussion to dot convention, we need to understand what a coupled circuit is. So I'll be writing some definitions and some notations here. I want you also note down in your notebook. So these are some good standard definitions to that will help you understand the dot convention more clearly. So first definition will be a coupled circuit. Okay, can anyone have an idea what does a coupled circuit means? When do we call a circuit is coupled? And any electrical circuit, if you take an electrical circuit is said to be coupled. Any idea when we call a electrical circuit coupled? We will call an electrical circuit coupled when there exists a mutual inductance between the coils present in the circuit. Let's say we have a complete electrical circuit. Let's say there are different coils in that circuit. Now, if there exists a mutual inductance between those two coils, then we can say that that particular electrical circuit is a coupled circuit. Now I will just gonna write that here. An electrical circuit is said to be coupled when there exists, what did I just say? When there exists a mutual inductance between the coils. Mutual inductance between the coils, that is not all the coils, whatever the coils that are present in that particular circuit, between the coils present in that circuit. Okay, now let's go right into the dot convention discussion. Now, now in this dot convention, we discussed a basic definition, but now we will even get a more standard definition for it. Now, this dot convention is a technique which gives details about voltage polarity at a dotted terminal. Because now, if you are trying to write a KVL equation for a circuit, for example, or we are trying to solve some nodal equations, or we want to write a KVL equations, the polarity of the voltage across a particular component is very important. Now, to know that polarity, dot convention helps us in finding that. Now, it is a technique which gives details about voltage polarity at dotted terminal. I'll just quickly write it. It is a technique. Now, the technique for what? Which gives the details about voltage polarity. voltage polarity at the dotted terminal. That's how this dot convention is important. Now we I will tell you two more rules later. Now, but if you understand those rules, we can easily tell the voltage polarity at the dotted terminal. About voltage polarity at the dotted terminal. Now, yeah, these are definitely important in while writing the KVL equation, as I said. Now, the two major rules which are very very important in understanding the dot convention. If you understand these two rules, there is no confusion will be there. So the first rule is, now let's say we take a coil. There are two coils in it. Let's take a circuit. There are two coils in it, and if current enters at a particular dotted terminal of one coil, let's say there are two coils, and if a current is entering at dotted terminal of one coil, then it will induce the voltage at the another coil, which is having positive polarity at the dotted terminal. I know it's a lot of terms I have used. Let me just write it and also draw a diagram for it, and you will easily understand it. The first rule, I also want you to note down in your notebooks because it's an important definition. If current enters, now this is important, if current enters at dotted terminal of one coil, I am assuming there are two coils. So of one coil I know dotted terminal, and if I see current is entering at that particular dotted terminal, then it will induce an voltage at another coil. Now it will induce an voltage, but what is the polarity? It will induce a voltage at the another coil which is having positive polarity at the dotted terminal. I will solve some basic equations, and we will discuss some good circuits also. It will be even more clear. We will come back to these two rules again and again, so it will be very clear. Don't worry. Which is having a positive polarity at the dotted terminal. So that is important. We know two dots and we can say the polarity terminal. Now, the second rule, if similar, it's just a reverse of it. Now, the highlighted point is it is entering here, and which will have a positive here. So those two are important. Those two are things you have to keep in mind. And the second one is, if current leaves if it leaves the dotted terminal, then you can guess it. What is the polarity of the induced voltage in the second coil? It will definitely be negative polarity. Now, if the dotted terminal of one coil, I can write it. Okay, I will just complete it two laws. Then it will induce a voltage at another coil which is having a negative terminal at dotted terminal. Now you have to keep in mind of this one. If it current leaves it, then it will induce a voltage. Whether it is leaving or entering, it will definitely induce the voltage. That's for sure. But what is the polarity of that voltage? That we can easily understand by these two laws. Now, I hope these two laws are very clear for you. Now, if we look into some more like detailing into it. What are different types of dot convention? What are different types of connections for this dot convention that we will see? Now there are two types of coupling you can ever find in this entire subject, or you can ever know there are only two types of coupling you can find. Any guesses? What are the two types of coupling? Yesterday we saw both coupling. Like last week we saw those both couplings. Can anyone tell me? Can anyone guess? Coupling classification. So there are two types of coupling. One is electrical coupling. And the another one is which one is left? Mechanical coupling. Sorry, so sorry, it's magnetic coupling. Yesterday we saw these two, right? I will get into definitions of these two as well, and we will solve some good circuits. You will understand it clearly. Now, electrical coupling and magnetic coupling are two types of couplings there exists. Now, electrical coupling, yesterday we solved but specific numerical also based on electrical coupling. Now, I will just give you the definition of an electrical coupling. So, electrical coupling, we say it will occur when there exists a physical connection between two coils. So if let's say a circuit and they are not isolated anymore, there is a physical connection between those two coils. So this coupling is called a electrical coupling. And even within electrical coupling, we have two types of coupling. That is aiding type and another one is opposing type. Now whether it's aiding or opposing, it will always depends on the current direction. If it is entering the dotted terminal or if it is leaving the terminal, then we can say it is a aiding type or opposing type. I'll just let's discuss first about electrical coupling, and we will see from circuit diagrams how it is a aiding or opposing. Now, as I said, electrical coupling is what it occurs when there is exist a. Today is all about some good definitions and also some standard circuit solving. I want everyone also you to note down these definitions, or also you can also solve with me for better understanding. So electrical coupling is what it occurs when there exists a physical connection between two coils. So you can see that the connection between two coils. Now this coupling can be, as I said, either adding or aiding or opposing. It depends on the current direction. Now let's draw the circuit for an aiding type. You can guess like what is the meaning of aiding. Aiding means you are adding to someone, like you are going along with it, not in the opposite way. So that's what we call a aiding type. Now we will see a circuit now, and I will tell you how it is a aiding circuit. And I have a circuit, one coil. I have drawn the coil 1, and this is a coil 2. Now this is a electrically coupled because I can see a physical connection. This particular connection actually connecting these two coils. So this is a electrically coupled coils. Now let's assume this is a polarity. I'm assuming. So I'm giving a supply like this to a circuit. If there is a potential existing at that potential plus and minus, now current will flow like this. Yeah, I am marking dots here and I am marking a dot here. Let's say I already know the dots. Now, if you see, there exists a mutual coupling between these two. That is the first definition we have seen where we will say a coil is coupled if there exists a mutual inductance between them. Now, between these two coils, apart from their self-inductance, there exists a mutual inductance. Now, what we call as a M, and they also have their self inductances L1 and L2. Now, I will say this is a electrically aiding coupling. Why it is electrically aiding? Can someone tell me? So these two coils are connected in series, right? Definitely they are connected in series. So since they are connected in series, same current will flow through both the coils. And in this case, I can see the current is entering at the daughter terminal of the coil 1. Let's say this is coil 1 and this is coil 2. Now in coil 1, I can say the current is entering at the daughter terminal. So let's go back to the previous slide and see the first rule because current is entering now. So if current enters at a daughter terminal of one coil, it will induce a voltage at the another coil which is having positive polarity at the daughter terminal. So if you see the coil 1 daughter terminal current is entering. Now it will induce a voltage which is definitely the mutual induced voltage at this particular coil where the positive polarity will be here at the dotted terminal and definitely the negative polarity will be here. Understood, right? So it's simple, like one based on current direction from one coil, we will see the voltage into the second coil. Now, what is that voltage? What is that induced voltage? It is M di by dt. I is the current passing through the coil 1. Of course, since it's a series connected coil, or both have the same current. So M di by dt. Now, another question, like another point we have to observe here is the same current also entering at the daughter terminal of second coil. So again, if you see the definition, since the current entering at daughter terminal of one coil, it will induce a voltage at the other coil having positive terminal at the daughter terminal and negative terminal negative at the other terminal. Now here also M di by dt will induce. That is because of the current flowing through the coil 2 and the polarity also now it's clear based on the rule. Now let's try to write the KVL equations. Okay. Now I will apply KVL here. Let's say I'm applying a voltage V and KVL equation I'm writing. V is equals to, you can also tell me what it is, L1 di by dt plus, I'm writing first the self-inductance parts, L2 di by dt. Now this mutual inductance parts. Now plus M di by dt plus another mutual inductance of both coils. Now, yeah, we have di by dt common and M is a common term. And if we see V is equals to, if I take that common, L1 plus L2 plus 2M total multiplied by di by dt. Now, this is what we call as equivalent inductance. Usually, in the numericals and all, in many problems in gate questions, they ask you to calculate the equivalent inductance when in electrically coupled coils, and you have to just calculate the inductances of self-inductance of both coils and the mutual, and the twice of it. It's very easy and standard numerical problem you can expect in gate. Now, people used to call this as a L equivalent, where V is equals to L equivalent into di by dt. L equivalent is L1 plus L2 plus 2. Why it is called aiding now? We have solved it and we have to say why it is aiding.
The mutual is adding, yes.
Right.
Voltage is added.
Yeah. And because of this mutual inductance, the total voltage induced by the self-inductances, and we are getting a twice of the voltage related to mutual inductance. So in total, we can see voltage is being enhanced, or we can say it's being added to the self voltages, self-induced voltages. So that's why we call it as a aiding. We will get even more clarity once we see the opposing kind of circuit, and you can easily expect also right now what will be the expression for the opposing type of electrical coupling. Anyhow, I will just write the circuit here and then we will quickly see the opposing type of electrical coupling. Yeah, in opposing type, the definition goes same. Like there is a electrically coupled coils are there which have physical connection, but the difference is the dot polarities will be different in this case. Now the same, I will take two coils which are physically connected, electrically coupled, or else we can call it like that. This is L1, this is L2, and I am okay. You carefully observe here. I am putting a dot of one coil here and the dot of another coil here. They are electrically connected. Same current flows through seriously connected circuits, but the dot polarities are different here. Now the mutual inductance exists between these two dots. Okay. Now we will see how the polarities change interestingly. Again, there is a input voltage V and current flows from positive to negative terminal. Potential, higher potential, low potential. Current flows in this path. Now let's see. If you see the KVL of this equation, yeah. Now if you see the KVL of this, now here look at the coil 1. The current is entering the L1, so it will induce a voltage in just right, coil 1, coil 2. So current is entering here, current is entering here. It will induce a voltage in the L2 having a positive polarity at the dotted terminal. Now where is dotted terminal? It's here now. The polarity will be plus here and minus here. The voltage will be same, m di by dt. Magnitude won't change, only polarity is what we have to decide based on the dotted. Okay, now let's see the coil 2 scenario. Okay, the current is passing in this way, and it is coming in this way, and it is entering the coil 2 and leaving the dotted here. Yeah, that's the only change from the aiding type circuit. Now, since the current is leaving the dotted terminal, it will induce a voltage in the other coil with negative polarity at the dotted terminal. Now, where is the dotted terminal in the coil 1? It is here. So, there will be negative here and positive here. Magnitude is same, md by dt. I hope it is clear now. It's nothing that confusing. It's only based on the current entering or leaving the dotted terminal. We can decide the polarity of the voltage induced in the opposite coils. Let's draw quickly. Let's write quickly the KVL equations. KVL, there is a voltage applied V is equals to self-inductance remains same, L1 di by dt plus L2 di by dt. So we have a negative mutual induced voltage for coil 1 and then another negative induced mutual induced voltage for coil 2. And then if we see the equivalent inductance in a opposing type, we can say L1 plus L2 minus 2M. So it's kind of opposing the voltage, whatever it is induced by the self-inductance. Now self-inductance and mutual inductance voltages are mutually opposing. That's why we call it as a opposing type of circuit. And here it is a again L equivalent but for opposing type. It's nothing very difficult. I hope this is clear now. Now let's look at the magnetic coupling. This is what actually happens in a transformer or any circuits you see. The winding is being wound on two cores. There is no physical connection between them. They are magnetically coupled. Magnetic coupling. So anyone will tell me the definition of a magnetic coupling? We just saw the definition of electrical coupling. So it occurs when there is just a physical connection between two coils. Then what is a magnetic coupling? So it occurs when there is no physical connection between two coils. That's it. When there is no physical connection between two coils. And even here as well, we will have two kinds, that is aiding type magnetic coupling and opposing type magnetic coupling based on whether the current entering or leaving the daughter terminals. Now, if we see like how the circuits change, how the KVL equations change, they are similar to electrical coupling, but we need to be careful of writing the polarities of the equations, and we will see how easy magnetic coupling understanding is also. Aiding type. Now, since the only difference for electrical and magnetic is there is no physical connection, so we can't write a series connected uh, coils. Instead, we will have to have a core in between, and we have to assume that there is a uh, magnetically coupled connection between those two. So, just like a similar like a transformer, this is coil one. That's a core on which these coils are wound, and this is coil two. They are now magnetically coupled, and this is coil 1, and I'm applying a voltage here, and there is another voltage on the secondary side, and the current flows through. I'm just applying voltage because we need to observe this phenomenon, current entering and leaving the daughter terminals. In order to flow a current, we need to have a supply. Okay, I am marking the here also there is a current. Now it is not same current anymore since they are not series connected. I have to call it as I1, and I will call this current as I2. And please pay attention while I'm marking the dots. I'm marking the dot of coil 1 here, and I'm marking the dot of coil 2 here. And the mutual inductance exists between these two, right? Now, current, look at the coil 1. Now, current is flowing through both coils, primary and secondary. They are I1 and I2 respectively, we gave. In this case, if you see the definition which we have wrote, the current is entering at the daughter terminals of both coils. Even for coil 1 and coil 2, current is entering at the daughter terminals. Now, hence, we can say that the induced voltages in each coil will be having the positive polarity at the daughter terminal because the current is flowing in the opposite coils. Now, the both currents are responsible for inducing the voltage at that particular daughter terminal. Now, because of I1, the voltage induced here will be M dI1 or I2. This is dI1 by dt. And the polarity is current is entering this dot. So the polarity will be positive at this dot. And it is negative here. Now here the magnitude will be M dI2 by dt. So current is entering this dot here. The polarity will be positive at the dot here. This is minus. Everything remains same. Nothing changes. Now, can you write KVL? No, but here there is no single KVL equation. We have to write two KVL equations for primary and secondary separately. Now, KVL at primary coil is simple. It's a V1. There are only two terms here, self-inductance and mutual inductance. L1 dI1 by dt, and the mutual will be there, which is positive here, M dI2 by dt, because the current responsible for inducing that voltage in the coil 1 is I2. Now the secondary coil voltage equations, if you see KVL, V2 is equals to L2 dI2 by dt plus M dI1 by dt, right? Now if you see the both equations, self-induced as well as mutually induced voltages have same polarity. Therefore, it is an example of a aiding, magnetically coupling of aiding type. Now, both self and mutual are actually aiding to each other and increasing the voltage, but not opposing to each other. That's why this is called a magnetic coupled circuit, which is of aiding type. Now, I will just quickly draw the opposing kind of magnetically coupled circuit. It's just the difference will be in the dot placement. Coil 1, core, coil 2, and I am applying voltage V1 here, current will flow I1, and applying voltage V2, current will flow I2, and I'm not changing the dot of coil 1. but I'm changing the dot of coil 2 here. Now the mutual inductance will exist M and this dot. They're coupled circuit now. Okay, now let's look at the terminals of the induced voltages. The current is entering in the coil 1 at the dot. Now it will induce a voltage in the coil 2, which is M di1 by dt, but with a positive terminal at the dotted terminal. You will have the positive at the downside here and the negative is at the leftover side. Now if you see the coil 2, the current is leaving the dotted terminal, so it will induce a voltage in the coil 1 having a negative polarity at the dot and positive polarity at the here, where the magnitude is M di2 by dt. Now let's quickly write the KVL equations of primary and secondary. The first coil V1, V1 is equals to L1 di1 by dt minus M di2 by dt, right? And V2, L2 di2 by dt, again we have a minus M di1 by dt. I hope this is very clear to all how the coupling works. So yesterday we were confused. Even if they're electrically connected, should we take the dot polarity here or there? What will be the polarity? I hope now it will be even more clarity for you. Whether it's electrically connected or it's magnetically coupled. Based on the dots, there will be definitely a mutual inductance between those two coils. The polarity will be decided of the voltage only due to the dots present there, not not any other parameter. So only important thing is locate where the dots are and see where the current is flowing, whether it's leaving or entering the dot, or correspondingly mark the voltage in the opposite coil. Even if it's electrically connected, there is no change. The loss remains same, and please carefully mark the polarities of the induced voltage in the coils based on the current entering or leaving the dotted terminals. Now, yeah, that's that's all I want to discuss on the dotted dot convention in a coupled circuits. So, two kinds of coupling: electrical, magnetic. Within electrical and within magnetic, we have two other types: are aiding type and opposing type. So that's it. Now you try to solve some more problems on the dot convention, specifically on this magnetic circuits. You will even get more clarity and better understanding, I suppose. Now let's go into the second week's discussion, which will be important for you to clear the assignments for this second week.
So something about the DC-AC coupling.
Sorry?
So is a DC current. I think it will not change or it will remain same.
No,
The
no, it will
DC
not
current.
change. It will not change. It will remain same. It will remain same. The polarity you have to take care, but the voltage remains there. So yeah, now even today also we will see the DC voltage applications of some coils. That will also help you. But today, the main discussion will be on very important rules that exists in the electrical engineering. We'll be looking at some basics of motor and generator, not specific to the AC machines. I'm not talking about specifically to AC, but on a motor and generator as a whole. All the, you can say, rotating machines. Now we will discuss two important rules that are often used in understanding the motors and generator concepts. Can anyone have a hint what those two rules are? Very important rules in understanding motor and generator.
Fleming's rules.
Yeah, exactly. So Fleming's rules are like a very standard and important rules in electrical engineering while understanding the concept of rotation in the machines, like how actually motors are rotating, how actually generator is generating the voltage. So to understand that, Fleming's rules are very important. We have left hand rule and right hand rule, and we will see those in today and how they are related to motoring and generating operation. That also we will see, and I hope you will get a even a better understanding. Now let's start with the. We will see. I'm not saying the name of the motoring or generating now. We will start with the discussion, and on the way of discussion only we will see which motoring or generating operation it is. Now, first law is, let's take a conductor, uh, a finite length. Let's say you know the length of the conductor as well, and it is moving with a velocity v. Um, okay, this is the conductor I have of length L. Okay, I know the length of conductor now. It's a L, and let there be a like it is moving with a velocity. I said now small v. Now let assume that this particular conductor is placed in a magnetic field along across this particular conductor. Now, if you can see me, I'm just holding this pen, right? Now, this pen is the conductor. This is the length of the conductor, which is L. I'm assuming it, and I'm placing it in a plane, and I'm moving it with a velocity v in a magnetic field. When I say magnetic field, above and below the pen, like this, there exists a magnetic field. Let's say this is the north pole, and let's say this is the south pole. You can feel there is a you can assume that there is a magnetic field around this particular conductor. Now, this particular magnetic field, what I assuming is north on the top and south on the bottom, so that always the magnetic lines will pass from north to south. Okay, now definitely if there exists a magnetic field, it will have its own strength. What do you call strength of a magnetic field? It's a magnetic field intensity. So how intense that magnetic field is. What is the name of it? What is the notation you denote a magnetic field intensity with? It's a capital B, which you call magnetic field intensity. And anyone can tell me the SI units of magnetic field intensity? It's a Weber per meter square, which we also call it as a Tesla. Now, I'm assuming the top, a north pole, the
Sir,
bottom,
B is magnetic flux density, na sir?
flux density. Yeah, yeah. Intensity is
H is
H.
magnetic
Intensity.
intensity.
Yeah, right. Flux density is B. Intensity is H. There is a mu naught factor will be there. Right, yours. I'm sorry. It's a flux density. How dense is the magnetic flux there? We call it as a magnetic flux density, and we denote it as, with a notation B, and the units are Weber per meter square, or we can also call it as a Tesla. Now, there is a north pole on top of the conductor and south pole on bottom of it. So the magnetic lines are flowing from north to south. And if you see the conductor here, all the magnetic strength is going into the paper. Now, let's say this is the entire paper or plane, you can suppose. On top of it, there is a north pole and bottom is south pole. And just you can't represent a 3D here. So the magnetic lines are going into the paper. On top there is a north and below the south. So if into the paper, we are taking the rotation as a cross, right? So all here magnetic field is present, and it is a into the paper, right? Now between these two end points of the conductor, what happens? Can anyone tell? Let's say this is a x and this is point y of a conductor. Now, can anyone tell me what happens between these two ends now? So, if you can see, the conductor is of a conductor is moving with a velocity, and it is having a magnetic field around it. And what happens is, between these two ends, x and y, an EMF will be generated. Okay, this between these x and y, there will be a EMF generated. And what is the value of this EMF? E. I'm calling the induced EMF as the generated EMF as a small e, and you know the B, and you know the length of conductor L, and this will the velocity V. So the value of the EMF will be E is equals to BLV. Okay, that is what the value of the EMF that is generated. Now, where the B is flux density, units are Weber per meter square or Tesla, and L is the length of your conductor, and V is the velocity. So if I am talking about SI units, everything should be in SI units. Weber per meter square, length should be in meters, and velocity should be in meters per second. So you take care of the units while solving the numericals. Those are very small things which we could make mistake while solving the questions. Now, okay. So now this particular magnetic field we have applied, and we have moved the coil, and there exists like we are assuming there perhaps there is a north pole above the paper, and below the paper there is south pole. Now these lines of forces, they are perpendicularly to the paper. Now, and this conductor is on a plane of paper, and we are moving this particular conductor with a velocity v, and between the x and y my EMF is being generated. So I will just write here. So this is my x y conductor, and this is the plane in which we are talking about, all the cross, and I'm moving this with a velocity v, and there exists a EMF BLV. Now, what is the polarity of this EMF? Is it plus minus or minus plus? You know the direction of movement, and you know the direction of magnetic field.
Why will be plus, sir?
Sorry,
Why? Why will be plus, sir?
at y you at y is plus.
Yes, yes, y will be plus.
Why? Like how can you tell that?
By Fleming right hand rule will come.
Okay,
Why?
okay, but what does a right hand rule say? Okay, I'll just it's other way around. It's positive at the x, and it is negative at the y. We will see the Fleming's right hand rule. The law I have said is correct. Now we have to apply the Fleming's right hand rule. Now everybody take your right hand, and you have 5 fingers, out of which we have the first one thumb, and you have a you call it a forefinger, and there is a middle finger. You take these three. Now we have to apply the right hand rule here, and right hand rule says if your forefinger denotes the direction of the magnetic field, which is B, and if your thumb denotes the direction of velocity V, your tip of the middle finger, it will give the polarity of the voltage induced, which is positive. Now wherever the tip is, it should be the positive polarity of the voltage induced. Now all these three are mutually perpendicular. I'm just drawing the figure also here. Now this is okay. It might not be that okay. Okay. So this is my right hand I place like this, and this is the thumb, and this is the forefinger, and this is the middle finger. Now, if thumb denotes the velocity direction, and your forefinger denotes the magnetic field direction, and your middle finger tip, that is this particular tip, will denote the positive polarity of the induced voltage. Okay. Now let's apply to this scenario here. With respect to x and y, if you see, where is my uh, let's start with the forefinger. It should denote the B magnetic field. Now here the magnetic field is into the paper. Now I have placed my forefinger into the paper. Okay, then let's see at the thumb, which should be the velocity. Velocity is from left to right, right? So into the paper, and I have velocity is this thumb, and now my tip of the middle finger is towards the roof, that is towards the X terminal here, this particular terminal here. I'm just trying to write the in with respect to the right hand rule. My thumb is here and forefinger is here into the paper, and I don't know, I can't write the finger here, excuse me. So thumb velocity, forefinger into paper, and the voltage induced will be at the tip of the middle finger, which is X, and here it will be positive and it will be the negative. So with respect to XY, if you see XY is here, and like you have a X and you have a Y, you are inducing a positive and negative here. It's like a, let's say you have like a kind of battery, if you say it's plus and minus. That's how the voltage of the battery will be BLV. The voltage of this uh, particular voltage generated will be BLV. Now I hope you understood this concept of Fleming's right hand rule. Right hand rule is correct, you have said, but you have to observe the directions. What actually denotes which finger denotes which one, and the placement of hand is also tricky. You have to place. You should not get confused. The thumb denotes the velocity, and forefinger magnetic, and tip of the middle finger should show the positive uh, the positive polarity of the induced voltage. Now, if you see in this particular expression BLV, if velocity is being constant, the conductors move with the constant velocity, and you are applying a constant magnetic field, B is constant and velocity is constant, length is always constant, then the output will be a constant voltage. Constant voltage is what? A DC voltage. Now, it's not alternating, and the output is a constant DC voltage if the velocity is constant and also the applied magnetic field is constant. So that's the Fleming's left hand rule. Now let's see the relation of this law with the motoring operation or generator operation. By now you can easily say whether it's a motoring operation or generating operation. But after discussing Fleming's left hand rule, we will note down all the key points at a same place, so you will able to relate it even much better. Now, before going into Fleming's this left hand rule, if you see if you see the magnetic field polarity here, let's say I'm reversing the polarity. Now I have placed the north pole on the bottom of paper and south pole on top of the paper. It will just the dots here instead of crosses, right? All the dots will be there, and dot means coming out, coming towards you. Now I'll just quickly apply the Fleming's right hand rule. My thumb denotes velocity. Velocity remains same, but now the forefinger is not into it but towards you. Now here, and right hand thumb denotes the velocity and magnetic field towards us, and the tip of middle finger is towards bottom, which is the positive polarity. It's bottom like this. Now then in that case, the positive polarity will be at the bottom and negative will be at the top. It's just if I'm just reversing the magnetic field here and there. Now I'm just telling you this because if you keep on changing the poles, north south, south north, north south, south north, you can see the voltage is being altered, right? When the north is on the top, you have a positive at the x. When the north is at the bottom, you have a negative at the x. So it's just I'm getting an alternating voltage by the changing in the poles position. So it's a very standard and basic understanding of how the alternating voltage can be generated from a conductor here. In future discussions, this conductor is nothing but a winding. So the basic understanding which we have to observe is Now, whenever a conductor is moving at a constant velocity v, will be having an induced voltage E, provided it is placed in the magnetic field B and the direction of B and V are always mutually perpendicular. So this is very important. Now the direction in which you have applied the magnetic field and the direction in which you are moving the coil should be always mutually perpendicular. You can't move both, you can't give a magnetic field and also move the conductor in the same direction. So that in that case there is no voltage induced. That voltage can't be generated in that condition. For example, if the conductor is moved vertically, now here I'm moving the conductor here, right? If I'm moving the conductor vertically, then there is no voltage because you must have a perpendicular component of your magnetic field with respect to the velocity. So then only your voltage will be generated, and then only the induced voltage will be present across this XY. So we'll come even better understanding in the further discussions. Few more weeks we have, many weeks we have. We will see that all. But for today, I hope you understood the concept of EMF generation from a conductor placed in a magnetic field and having a velocity v. Now, let's look into the next other rule. But now, similarly, the cases all will remain same. And but here we are not generating it, but instead we will give a supply, and we will see then what new law we can get from that. And the second one, similar condition, we have this conductor of length L. We'll take XY, same, no confusion, and it is having a length L. And once again, assume the same magnetic provision, that is in north at the top above the paper and south on the below. And now if you do like that, the magnetic field will be cross, right, north to south. Now to the end of this wire XY, let's connect a supply. Okay, I'm just connecting this to this and this. I am actually connecting a source. This is positive minus of the source. So current will flow from here to here through this conductor, right? Current is I, that is flowing through the coil. When I connect a source through a conductor, current will flow in the circuit. I'm calling that current as a I. Now the law is, whenever a conductor is carrying current and there is also a magnetic field perpendicular to the direction of the current flow. Now the current is flowing in this direction and my magnetic field is in perpendicular direction from top to bottom. Then what happens? A current carrying conductor placed in a magnetic field and the magnetic field is perpendicular to the direction of current flow, then the conductor will experience a force. That's the law. Now the magnitude, what is the magnitude of the force and the direction of the force? So those are our point of interest. And to know that, we will use the Fleming's left hand rule. Again, I'm repeating the law here. When a current carrying conductor is placed in the magnetic field and the direction of magnetic field is perpendicular to the current flow direction, then the conductor will experience some force. So now what is the magnitude? This is the force F, and what is the magnitude and direction of the force? Yeah, we know the B, we know the current, and we know the length L. Now the magnitude is, you might have heard, the formula is BIL, right? Now to know the direction, we will use the left hand rule. So everybody take your left hand and keep it all the three fingers mutually perpendicular to each other. So definitely the current and the magnetic field should always be perpendicular. That's what the rule also says. Now the forefinger, which is the first finger, just turn this finger beside the thumb, it will denote the B, same as the right hand rule. The forefinger will denote the direction of the applied magnetic field, and the middle finger will denote the direction of current, and the resultant force direction will be denoted by your thumb. So that's what Fleming's left hand rule says. Now I'm drawing the left hand rule here. This is my thumb, and this is my forefinger, and this is my middle finger. And if my I'm just noting the notations here. If my forefinger denotes the direction of B, and if my middle finger denotes the direction of current, and my this particular thumb will denote the direction of the force. Now, in this scenario, if you see, can you tell me what are the directions of our notations here? Now, we have a current direction from here to here, right? Okay. Now, from right to left, current direction is here. I have taken the middle finger here, and the magnetic field is into magnetic field is nothing but forefinger. Okay, into this one. Magnetic field in this direction, and middle finger is current, and the thumb will show you the direction of the force. So which is the towards the bottom, the force experienced will be in this direction. So the thumb is showing the force, and the forefinger is showing the magnetic field, and the current is showing this in this direction. So that's what this is. Now, using the left hand rule, you can find the magnitude and polarity of the force, and using the right hand rule, you can find the polarity and magnetic of the generated voltage. Now I'm just writing the key points as a conclusion here. It will be important for you to remember. Fleming's rules. First one is right hand rule. Now, right hand rule is used for calculating the estimating or finding anything. Polarity and magnitude of generated voltage. And left hand rule polarity and magnitude of the force. Yeah, here polarity means nothing but the direction of force. Okay, now can someone tell me which law relates to which machine? Which law is related to generator and which law is related to motor? Okay, right hand rule is related to generation or motor operation.
Sir, right hand rule is related to generator, and the left hand rule is related to motor.
Right, exactly. Thank you. So in the right hand rule, you usually use the right hand rule to find the polarity and magnitude of the generated voltage. So there you are actually generating voltage by just giving a magnetic field and moving the conductor with a velocity. Now it says that if you can move that kind of conductor in a magnetic field with some velocity, you can actually generate a voltage. When you are generating the voltage, it's related to the generator. Now in the left hand rule, you actually try to see the direction of force when you are externally providing a supply and you are externally providing a current to flow through it. That's what motoring happens, right? For the motor to rotate, you will give a supply, and when you give a supply, there will be a rotation. Rotation here itself is the force. Now That's why the left hand rule is kind of a motoring. So this is important concepts when it's related to the electrical machines. It's not just for electrical machines 1 or machines 2. For all the rotating machines, these laws are very important. And I hope you got the clarity in Fleming's rules and what is right hand rule, what is left hand rule, and when to apply it, and what exactly is the rules. That's what the important point is. So whenever you are asked what is left hand rule and right hand rule, you should tell them along with the definition when a current carrying conductor, so, 1 second, when a current carrying conductor placed in a magnetic field that is perpendicular to the direction of current, definitely there will be a force experienced by the conductor. Now, similarly, the other rule where when a conductor is placed in a magnetic field and it is moved with a velocity v, then EMF will be generated. So these are important rules, and you have to remember it. And the formulas also. Formula for generated voltage is BLV, and formula for force experienced is the BIL. So if there is an alternating component, if there is an alternating or B and V are alternating, then we also have these formulas changed. There will be a theta term, sin theta or cos theta that will come later, but these are basic understanding. So this, if you are clear it, then there is no difficulty in just understanding the concept for alternating concepts. Because just now we saw if it's a cross and if it's a dot, the poles are being changed in north and south, and you are getting a reverse polarity of plus and minus. So it's simple understanding of it. And with this, let's start solving some important, or I can say very simple formulas. Sorry, numericals. These are very basic questions only. You don't need to read by seeing the diagrams or something. It's very whatever we discussed, they are just representing that in the 3D form. We just did it in the 2D. So no worries. So yeah, let's take your pen and paper. Try to solve it with me, and very pretty simple. The formulas which I have discussed, the concepts which I have discussed, on those only the problems are here. So let's solve with it. Okay, now let's read the question. Before going to the question, we see equipment here, where the north pole is at the bottom of the conductor plane and south pole is at the top of the conductor plane, and we can see the magnetic lines of force, the arrow marks are from north to south, and at the end of this rail means whatever path the conductor is being placed, there is a resistance, so such that maybe if any current passes, there is a load to take that. So yeah, okay, there is a resistance R, and there is a conductor AB. That AB is the conductor, and someone is pushing that conductor from left to right, and that's all the equipment is. Now let's get the question. Now consider the thought experimental setup. Thought experimental means assuming some setup like above, and we were given the length of conductor, that is 0.4 meters, and the flux density D, 0.8 Tesla or Weber per meter square, and the resistance is 1 ohm. All other resistances are negligible. All frictional forces are negligible. This is very important information to be given. Considering the resistances and frictional forces, the entire formula will be different, because whenever the current conductor is flowing through the rail, there are many resistances which will face. First one is the air resistance. There is an opposing force of the air, and there is between the rails and the conductor. There will be a friction, right? All the other resistances should be negligible. Then only you can able to understand this loss better in the applicability of the loss to for the better understanding. But in reality, they do exist. They are definitely exist. So that's why when we talk about machines later, we have to consider all these parts, and usually we model it as a losses. If you remember, the frictional losses and windage losses, everything will be there. But for the ideal purpose, to understand the loss better, we are assuming that as negligible. Okay. Now the other part of the question I'm reading. So the conductor is pushed with a constant force of 100 millinewtons. So we were also given the value of force also. So no need to calculate the force. And therefore, at steady state, the conductor will move at a constant speed, velocity is constant, and a constant EMF will be induced in it, which will drive a constant current through the resistance. Okay, that's what the law says, right? We just discussed whenever we are providing an external source and current is being passed and the conductor will experience a force. Now, what here happened? We are providing the force. Externally, the force is being provided. When it's other way around, when we are pushing the constant conductor with the force, and then it will drive the current. That's vice versa. So okay, now let's see what the question is. The question is we have to estimate the current that will flow through the resistance in the steady state. Okay, we just have to find the current that is being generated because of the force we have applied. Okay, now I'm trying to solve. I hope you got the idea already how to solve this because you know the force, you know magnetic field density, and also the length of the conductor. We just need the current only, right? It's left hand rule. Now at steady state, force is equals to BIL. I is what we need. B, L, and F are known. I is equals to F by BL. Now F is what? 100 millinewtons. I'm conducting or converting into, of course, SI only, millinewtons. And B is in how much? Tesla, it's also in the SI unit. Tesla is SI only, it's nothing but Weber per meter square. And length of the conductor is zero point 0.4 meters. Okay, this is also in the SI unit. So, how much is it? Please solve it with me. If you have calculators or anything, you can just try it. Okay. It seems like my calculator is not working right now. Let me just use my mobile. 100 divided by 0.8. Okay, anyone got the answer? You need to observe that in the question also they are asking the current in milliamps only. So you make sure the 10 power minus 3 stays there. Even the gate also, the units are very important because they might ask it in amps or might ask it in milliamps. So even if you solve the entire question correctly, just because of that unit they have asked, it could go wrong. So read the question very carefully. So I'm keeping this my 10 power minus 3 as it is. So I'm getting 312.5 into 10 power minus 3 amps. So it will be 312.5 milliamps. So I hope you also got same answer. Simple one. You just have to calculate the current. Now we have to estimate the induced EMF. That's also in millivolts under steady state condition. Okay. Now, what is the law related to the EMF that is being generated? That is right hand rule, right? We already know the formula for induced EMF or generated EMF, which is E is equals to BLV. Now, what is the problem here? To apply this particular formula, E is what they are asking. BLV. There is no problem. B I know, L I know, and E is what they have asked, and I have no information on V also. I don't know with what velocity the conductor is being moved. So no point in applying this formula. But of course, we already know the current that is being passing through the load, which we have just calculated using the left hand rule. Now you have to calculate the E, but by seeing the figure, there is a resistance which I already know the value, and I also know the current flowing through it, and I just have to calculate the E. Simple Ohm's law. Now based on that, E will be how much current I got? 312.5 milliamps multiplied by 1 ohm resistance. Now the question already asking you in the millivolts only. So it will be 312.5, yeah, millivolts. Same thing. That is what the EMF which will be induced under steady state motion. We use this formula only because we know the current, we don't know the voltage. We have an advantage of knowing the current before. So that's why we know. If we don't know the load value, we can't use this formula. See the next question, as expected, it is about the estimating the steady state velocity. Now since we are at advantage of knowing the induced volt EMF already, now it's simple, the right hand rule formula only. Now steady state velocity, see, you have to observe it. They are asking in the centimeters per second. It's not meters per second. So you have to keep in mind. Now, you know the formula of that particular right hand rule. E is equals to BLV, and V is what they are asking. And you know the E, and you know the B, and you know the L. Now, velocity is equals to E by BL. What is the E? It is 312.5 millivolts, and B is how much? Is zero point 0.8 Tesla, and length is 0.4. How much is this? 0.8 divided by 0.4, and I got 976.5 into 10 power minus 3 meters per second. Okay, now I just have to convert this into a centimeters per second. 96.5 into 10 power minus 3 into 10 square centimeters per second. So it's 97.65 centimeters per second. So that's it. It's simple application of your loss, and we calculated this. Okay, we just have the information about the EMF. That's how simple we could be able to calculate the velocity. If we don't have the EMF, definitely it will be problem. In the question, we are given everything. What is the resistance? With what force you have pushed it, and magnetic density, and also the length of the conductor. Everything is given. So simple values. Now let's look at the last problem for today. That is estimate the power again in milliwatts that is required to keep pushing the conductor at the steady state. Okay. Now we were being asked the power which will be needed to keep pushing the conductor. Okay. Now we know some formulas related to power. That is I square R. You know, that is basic V multiplied by I. You know, I square R. You know, but apart from these two, there is another formula for power when you know the force and velocity. Force is in newtons and voltage is in meters per second, and the power is in watts. So what is the relation between power, force and velocity?
FV.
Yeah, power is equals to force multiplied by velocity. So this will be in watts, and this will be newtons, and this will be meters per second. Okay, now we will verify in the with all the three formulas. We will verify it should definitely come the same, but I'm just utilizing the data which we already know. Now power is equals to force into velocity. What is the force? It is pushed with a 100 millinewtons multiplied by velocity. What is the velocity we got? Steady state velocity is in meters per second. I need, so 976.5 into 10 power minus 3. So this is one velocity which we got. They are asking in milliwatts, so I'll keep 110 power minus 3 as it is, and there is a 100 here, and there is a 10 power minus 3 minus 1. So it's 97.65 milliwatts. That is the power required to keep pushing. Now we already know some basic formulas for power. That is I square R, and one is the VI. Now I, you know, right, how much current? Current we know it's 312.5 milli you 312.5 multiplied by 1, and E also same 312.5 millivolt into 10 power minus 3, and current is 312.5 into milliamps. So now if you see these two are already same, and you just have to solve these two, and I'm sure you will definitely get the 97.65 milliwatts. So yeah, these are some. I think that's the last question for today. Yeah. So yeah, utilizing the basic laws of left-hand rule and right-hand rule and force experienced by the conductor, induced EMF generated, and everything using these concepts, I'm sure these problems will feel basic and simple. And let's have a quick summary of today's discussion, what we have discussed. And we started our discussion with preliminary extended discussion of the last week discussion, like where we have some basic confusions about the dot convention, if it's a physically connected and if it's not a physically connected. So we looked at started with the basic definition of what the coupled circuit is, and again a coupled circuit is what a if there is exists a mutual interest between two coils, and we definitely call that as a coupled circuit. And then we started dot convention discussion. Dot convention, the big and important two rules A and B. Please remember these two. If the current enters a dotted terminal, it will induce a voltage at another coil having a positive polarity. If the current leaves the dotted terminal of one coil, it will induce a voltage at the other coil which is having a negative polarity. These two laws are also applicable in both electrically coupled and also magnetically coupled. So no matter what the coupling is, connection is, these two rules will apply. Now yeah, then we saw the classification within coupling, electrical and magnetic. Electrical and magnetic have both two sub parts, I can say, that is aiding, opposing, and magnetic coupling also has two parts, aiding and opposing. And yeah, so we saw this how aiding works, how opposing works, and based on the electrical connections and magnetic coupling circuits, we solved the KVL equations, and we saw how aiding type equation would look like, and how an opposing type equation would look like. And then we discussed about magnetic couplings circuits and how a magnetic coupling circuit would look like, and based on dot terminals, how the induced mutual inductance voltage will be. And just looking at this slide itself, we can say the self and mutual are aiding each other in the top two equations, and self and mutual are opposing in the bottom two equations, and that's how it is. And yeah, we have then we started our this week's discussion on basic and important two laws of machines, which are Fleming's left-hand rule and Fleming's right-hand rule, not just AC machines, but all the rotating machines. And what is a left-hand rule and what is a right-hand rule? We started with this particular right-hand rule where the law says whenever a conductor is placed in the magnetic field and moved with a velocity v, EMF will be generated. The given that point is the direction of voltage and the direction of magnetic field applied will be always mutually perpendicular. And we saw how the voltage is being generated, and we also saw the potential reversal when we have reversed the magnetic field. So that's one important question. Even in GATE, for 1 marks or 2 marks questions, you usually get this. So in a machine, if you want to reverse the polarity of the generated voltage, what to do? One option will always be there to reverse the magnetic field applied. So that's we saw today, and that's a Fleming's right-hand rule is applied for the generator. And yeah, then we saw the Fleming's left-hand rule that is applied for the motoring operation, and it says that whenever a current carrying conductor placed in a magnetic field it will experience as a force. And using the this particular left hand rule, we can find the direction of the force. So these are the basic laws, and I hope it is clear for you now which law is for which and which law is for which operation. It should be easy for you to relate. And then we started solving the problems. It's a thought experiment setup. We saw how conductor is being pushed on the rails, and there is a load connected to it, and a magnetic field is applied. If we reverse the polarities of north and south here, you will see the reversal of polarity. So the current won't flow from like A to B, or it might flow from B to A. So the current flow will be different if that's reversed. So we solved some basic problems, and then we saw how with just equations of F is equals to BL and E is equals to BLV, we can solve the required questions. So one more thing, if there are two unknowns in the equations, if you are stuck there, and using the basic Ohm's law also will help you in calculating the current that is being uh, induced EMF that is being used. And yeah, that's it. And we solved the velocity and also the finally the power equations. So the power being very cross verified with three different formulas. One used force and velocity, one with the I square R and EI. So yeah, we will in the further weeks we will extend this discussion into a in-depth machine-based discussion where we will discuss the windings of a machine, how the windings of a machine should be, what are the how a construction of a machine will happen, and what are the losses involved in a machine. It will be a very good discussion we will be having this semester, and I expect every one of you to attend it and participate in the discussion and make this session even more interactive. And before concluding the session, I would like to ask if there are any doubts related to today's discussion. You can ask.
Sir, excuse me.
Yes.
Last week we had one doubt, na, sir, related to the dot convention.
Yes. Yes.
That transformer, that
In that,
artificial connection of windings.
yeah, that's what we have discussed today, right? If it even if it's a magnetically coupled circuit, even if there is no physical connection, based on the dot polarities, you can decide the polarity of the voltage. So whatever the current flowing only, if the current is entering the dot or leaving the dot, only that will matter.
Okay. So don't bother about that bottom connection, closed
No,
connection.
no.
Okay.
That's what electrical coupled circuit and magnetically coupled. Even if there is a physical connection, even if there is not a physical connection, if there
Okay.
exists a mutual inductance, if you see two dots, then they
Mm.
definitely mutual inductance will be present in that circuit, and based
Okay.
on that only you have to decide the polarity of voltage, not based on the physical connection.
Okay. Thank you, sir.
Welcome. So yeah, uh, any other points to discuss today? Okay. Uh, Thank you all for attending today's session and actually participating in this discussion. So yeah, we will meet again tomorrow for the sorry